so we are in causal inference in statistics primer, and we are on question, what are we on? Question 1.51. Okay, so this is a multi-parter, and some of the parts are pretty interesting. So what applies to everything is, suppose that we have the following structural causal model, okay, given here. All right, so we have our variables x, y, z. We have their individual error terms, ux, uy, uz, okay? And then their functions, f of x, where f of x is given here, where x is just equal to its error term, f of y, where y is equal to this function, and f of z, that is equal to this function. Okay. Assume all exogenous variables are independent and that the expected value for each exogenous variable is 0. So what are the exogenous variables? It's these u variables here. Okay. An exogenous variable is a variable that doesn't have a cause, at least within our model. Okay. So we'll go through all of these parts. The book lists a part F, but part F is just part C, so I think it's a typo. So I put it in here just for completeness, but I think it's already done in C. Okay, so for part 1, we are meant to draw a graph that compiles the data, okay, or at least the description of the data that we're given, okay. And this is what we have. So we have our variables x, y, z. We notice that x is just ux, right? So we have x, and we see that its only contributor is u sub x. We have y, and y is equal to, well, it's a function of x and its own exogenous variable. So here's y, it's a function of x and u of y. And then we have z, and z is just a function of y and its exogenous variable. Okay, and so that's our DAG. Okay. So now, in the next several parts, we will actually generate data from here and then simulate it. And so that's all that this block here is doing. Okay, so I'm going to simulate, let's see, 100,000 different observations. And so I have my variables u of x, and it has an expectation of 0. And because later in the problem we're told that we are meant to assume that the u of x's are normal distributions, I'm just plugging that in here from the beginning. Okay, so the u of x's are all standard normal variables, mean mu, or mean 0, standard deviation 1. And then of course x is just u of x, right? It's just its own function up here. And similarly for y and z, so I'll just use those functions in creating them here. Okay, so there's our data set. I put it into a data frame here if that's easier for you, but I don't think I actually ever used a data frame. But okay, so the first one is we want to determine the value, the expected value for z, given that we observe that y equals 3. Okay. So for this, we want to find the function of z, and it's right here, reproduced right here, and we see that it's y over 16 plus u of z. Okay. So for each of these, we're going to solve it both by using linear expectations as well as linear regression. Okay. So let's start with the linear expectation. So if I want the expectation of z given y equals 3, well, that is the same as the expectation of y over 16 plus u of z given y equals 3. Okay. And with expectations, I can take constants out. And so 1 over 16 is a constant, so I take that out. So I have expectation of y given y equals 3 plus the expectation of u of z given that y equals 3. Okay. So this guy right here, the expectation of y given y equals 3 is just 3, and it's multiplied by 1/16, so I have 1/16 here. And then the expectation of u of z given that y equals 3 is just 0. Okay. Why is it 0? Well, we know that u of z is distributed normally with a mean 0 and standard deviation 1, so its expectation is 0. And when we condition on a particular value of y, it's not doing anything to our expected value for u of z. And so you can kind of see that in our diagram here, right? So y is in no sense a cause of z, or u of z, I should say. Okay. All right. So as a second approach, we will use regression. Okay. So now we say that the expectation of y, or of z given y, is equal to our linear combination here. Okay. Where the beta term is given by the covariance of z of y divided by the variance of y. And then alpha is just going to be the expectation of z minus beta y times the expectation of y. Okay. So I won't go through all of the math here, but you should be able to follow it. Okay. And what we get in the end, well, we get a few things. We get that the variance of y is equal to 10 over 9, and we get that the covariance of y and z is 5 over 72, and we get that the beta coefficient, this guy right here, is 1 over 16, and we get that the intercept, alpha, here, if we just run through everything, is 0. Okay? So the expectation of z given y equals 3 is, well, so we have the beta, so alpha is 0, beta is 1 over 16, right? That guy is 1 over 16, and y is 3. So we get 3 over 16. Okay? So we can actually simulate this. So I'm gonna simulate this. So here I'm just running regression of z on y. Okay, and so this is the R command for it. Okay, and so here I'm just putting in the calculated values for expectation, variance, covariances, beta coefficient, etc., as well as the simulated values for everything. Okay, and so so again, I won't go through all of this. It's just showing different ways that we could have approached this problem. Okay, so anyway. So we have our calculated expectation. That's what we were asked to find. So this comes out to the fraction of 3 over 16. When we used our simulated data, we came reasonably close. But again, actual data in the real world is going to be messier than perfect thought experiments. Okay, so these are fairly close, and you can again go through everything here and just see how close the simulated values, the calculated values, etc., are. Okay, as well as well, anyway. Okay, so now we're on to C, and C is very similar to B, so we're going to determine the best guess of the value, the expected value of Z, given that X equals 3. Okay, so we'll go through this even more briefly. So this is very similar to the first, or to part B here, except now we have that Z is this, but we also know that Y is a function of X, right? We know that Y is a function of X. And so we're just going to plug this in for the value of Y in the formula that gives us the expected value of Z. Okay. So there's a little bit more arithmetic involved, but the steps are the same. Okay. And so first we go through with the linear expectation operator. Okay. And we come out with 1/16, and this is later verified both when we run a regression on simulated data, as well as when we calculate by hand the regression coefficients. Okay, or when we calculate the regression coefficients and then calculate expected value of z given x with this formula here. Okay, and then this is all the components for regressing z on x. Okay, so we find beta x, which is just the covariance of z with x and the variance of x, and so on and so forth. So again, I'll let you piece this together on your own. Okay, but in the end, the question that we're really meant to answer is, what is the expected value of z given that x equals 3? By our regression calculations, we get 1/16. That's the same answer that we got for the expectation, or the linear expectation, or the simple expectation operations. Okay. And when we actually run regression, that's also what we get. Where are we here? Yeah, so with simulated expectation. Okay, so we get about the same values, right? So this decimal is about 1/16, or this one is exactly 1/16. This one is approximately, because it's done with simulated data. Okay, so parts B and C were fine, and so now we start to get a little bit tricky. So now we're trying to find the expected value of z given two other variables, x and y. Okay, so there's a couple things that we could do here. But the thing that we should immediately grab onto is, let's go back up to our DAG here. Okay, so we're trying to find z here given x and y. Okay, but notice that that y directly affects z, but x only affects z via y, right? And so once we know the value of y, the contribution of x is, I don't want to say it's canceled out, but it's accounted for in the value of y. Okay, so so really the question that we're being asked is the same as give me the expected value of z given y. Okay, again, it's because the contribution of x to z is via y, and we're already told a value for y. So any contribution that x has to z is accounted for in y already. Okay, so let's scroll down here. Okay, so since we already found the expected value of y, or of z given y equals 3 here in part B, right, and that value is 3/16, we should obtain the same value for this problem here. Okay? And so rather than go through all of the math for it, I'm just simply simulating it. So now I have a simulation of z with x and y. Okay, and so again, we expect this to be about 3/16. So let's go through this. Okay. So here I wish I hadn't printed that here. Let me run that without printing the summary output. That's not really important here. Well, no, actually it is. Okay. So let's go through all of this. Okay. So this part right here is gives us the summary of our regression. All right. So here's the here's the coefficient for x and for y. Okay. And for the intercept. Okay, so notice that the coefficient for x is basically 0, which it should be. Okay, again, it's not perfectly 0 because we're using simulated data here. All right. But anyway, when we go through and we try to find so when we have the expected value of z given y, we get this fraction, which is about 3/16, right? Which is what we found above. All right. And then when we simulate z given x and y, so this regression right here, the multiple regression, okay, where x equals 1, we get basically the same value. It's not exactly the same value because in our simulated data, even though we know, because we made the data, or we created the simulation that made the data, even though we know, for instance, that this value is actually 0, but for random sampling variability and sampling bias. Because of that, we know this value does not exactly match this value, right? So there is some pseudo relationship between x and z even after accounting for y, and that is just sampling bias. And we can expand, so we can like magnify that sampling bias if we set x equal to 10, and you see that pseudo relationship between x and z starts to blow up the expectation of z, but the extent to which this is above 3/16 is just due to sampling bias. Okay. Now for part E, we're told to assume that all exogenous variables have a variance of 1. Okay. We've been assuming that this whole time just so that I could do these simulation regressions and everything. Okay. And so it doesn't hurt anything, but now that is made explicit. And so now we're asked to determine the best value of x given that we observe y equals 2. So let me start by pointing out that this is a different question, a different type of question than what we've been asked. So far we've been asked questions like, what is a variable given one of its causes, right? What is the value of y given x? What is the value of z given y? But now we're being asked something different. We're being asked, tell me the value of the causal variable given the effect variable. Okay? So I'm just flagging that. All right. Go down, go down, go down. Okay. So again, we're going to use both ways of solving this. We're going to use simple expectation, and we're also going to use linear regression. But I'm going to start with linear regression because in this case, even though the math has up until now been more convoluted, it's actually simpler in this case, okay? So if I have the expectation of x given y, it's going to become this, this equation right here, and we can get beta y, it's just this right here, so on, so on, and so we've ultimately, what we get is that the expected value of x given y equals 2 equals 0.6, okay? Again, I'm just skating through the math there, but it's all there for you to look at and examine and make sure that you can reproduce it, or to tell me if I'm wrong, if I've messed something up, which is possible. And so I'm going to simulate this as well as a way of verifying my math. Okay, so now I'm regressing x on y with this formula right here, and then I'm just going to give the expected value when y equals what is y supposed to equal? 2? Yeah, when y equals 2. Okay. Oh, I guess I've already done this, and it's 0.6 ... which is what we solve for analytically. Okay. So now let's go back to using just simple, oh well, it's not so simple in this case, but just using just simple expectation operators. Okay. So now I have the expectation of x given y equals 2. And so what I'm going to do is I am going to solve for x given the formula for y. Okay. And so when I do this, x equals 3y minus 3u of y. Okay. All right. So so if I want the expectation of that, it means I want the expectation of 3y minus u of y, given that y equals 2. And so now I'm going to separate this and this expectation. So I have the expectation of 3y given y equals 2 minus the expectation of 3u of y given y equals 2. I can take the constants out front, right? So I'm taking that 3 and I'm putting it out front. Okay. And so now we have the 3 times the expected value of y given y equals 2. Well, obviously that's just going to equal 2. And I'm multiplying that by that 3 there. Okay. And now I have 3 times, and this is where things get sticky. The expected value of u of y given y equals 2. All right, so now your first instinct might be to say, well, 0, right? Because we're told that u of y is distributed normally with a mean of 0. Okay, but that's not correct here. I'm going to explain why that's not correct. The reason that it's not correct is the same reason that this entire problem is a little bit unique. Okay, the reason it's unique is because u of y is a cause of y. Okay, so just like x is a cause of y, right? So again, in this problem, we're being asked to give the expected value of the causal variable given, right, given the effect variable. Okay, so the reason that this is tricky in this particular instance is because the effect variable has more than one cause. It's x and u of y. And so if I know the value of y, right, that means that the values of u of y and x, they're going to be linked, right? They have to coordinate in such a way that y equals 2, right? So if x equals 3, u of y has to equal 1, right? So so that's going to throw a wrench into how we go about solving this. Let me scroll back down here. Okay, so there's a couple of ways to solve this, and the first way is I'm going to solve it analytically, and this is correct, and in fact, this is probably how you would be shown to solve this in a class, but it also doesn't offer a lot of insight into what's taking place here. Okay, so to solve this analytically, we want to know this generally. So if I have 2 variables, call them a and b, and they are normally distributed, and not only that, but they are jointly distributed in a bivariate normal distribution, okay, which we are assuming here because of the question. Well, then the expected value of A given B is equal to this expression right here. It looks a lot like the regression formula, doesn't it? Okay, the one difference being that instead of, well, the one difference being that this guy right here is taking B minus the expected value of B rather than just B. Well, and so anyway, but so if I just simply blindly apply this formula to what we want, where now u of y is A and y is B, I can just go through, churn through, churn through, churn through, and what I get is that the expected value of u of y given y equals 2 is 1.8. Okay, and so if I plug that back into the thing that I'm trying to solve for, I go through. Remember, this was the sticking point. Okay, and we just found that it's 1.8, and so when I plug it in here, I get that the expected value of x given y equals 2 equals 0.6, and that matches our regression method that we found up here. Okay, so we should have some confidence that we've done this correctly. Now, that's fine and good, but this method does not really illustrate the thing that I was trying to show earlier, which is why this problem is unique. We're going from an effect variable and trying to infer the value of a causal variable. Well, okay, this method does not show that, and so I want to show that relationship between u of y and x, given we know the value for y, where here y is equal to 2. Okay, so we can do this in a few ways, and so the first thing that I'm going to do is I'm just going to plot y over top of u of y of our sample data. Okay, so remember we've generated some fake data, and then I'm going to color x such that small values are red and big values are green, and we're going to find a relationship here as soon as this runs. Okay, so let's just look at what we have. So on the y-axis we have y, and then on the horizontal axis we have u of y. Okay, and so notice that and all of this colored region is the data points. Okay, and now I've drawn a line at y equals 2. Okay, so all these values are y equals 2, and then I've color-coded the individual data points. Okay, so you'll notice that for smaller values of u of y, okay, we need larger values, they're green, we need larger values of x. And as the value of u of y increases, we need smaller values of x to stay on this line where y equals 2. Okay, so that's one way of looking at it. Let's look at this in a different way. So now I'm going to plot x and u of y, okay, and then I'm going to, well, I'll show you what I'm going to do, but I'm going to draw a line where y equals 2, okay, and so you can look at my code here to see the math that I used to find that line, but we're gonna draw that, and we're going to look for some more relationships. Okay, so here I have my data. Okay, it's the same data as up here, but now I've plotted different variables. Okay, I have u of y on the y-axis and x on the x-axis. Okay, these white lines here are contour lines. So as I go more towards the center, the probability of that particular of data points of that value are increasing. Okay. Notice that 0, 0, and both x and u of y have expected values of x. Okay, and red signifies how close that particular value is to y equals 2, and as it gets blacker, you're further away from y equals 2. And exactly y equals 2 is represented on this line, on this black line here. So once again, notice that as I go to larger x values, right? As I'm going right, I also have to go down in the u of y values. I need smaller values for u of y to stay on the line for y equals 2. Okay. Similarly, if I use bigger values for u of y, I have to move left and get smaller values for x. Okay. And this is the relationship that I'm talking about that is being induced between u of y and x, even though u of y and x don't cause one another or anything, but we've conditioned on their common cause, on y. Okay, so what this suggests is if we want to find the expected value for u of y when y equals 2, we need to take into account the joint distribution that is between u of y and x when we know that y equals 2. Okay, so that's what we're going to do here. All right. So what I'm going to do is I have a bunch of values for u of y and a bunch of values for x. Okay, so I just define values from -3 to 3 for u of y, and then I calculate the necessary x value such that y will equal 3. Okay, which again, or I'm sorry, y equals 2, which again is 3 times y minus u of y, and so here u of y is u of y seek. Okay, and then I'm going to sum all of this. Okay, as the formula for y. Remember, y is x over 3 plus u of y, so I'm just going to do that, and you're going to see that every entry is 2. Okay. Now, what I'm ultimately going to do is I'm going to sample u of y, but I can't sample u of y from its own distribution, right? We have to take into account the joint distribution between u of y and x. And so to create that joint distribution, I have this right here. Okay, so I'm just multiplying the probability distribution of u of y as well as for u of x, or I'm sorry, for x. Okay, and I'm going to draw my samples from there. I've also done it for x, but we don't need them. And then I'm just going to look at the average, the mean of my u of y samples. Okay, so let's go through that. All right, so again, first of all, remember that, so all of these 2's, like I said, I'm going to calculate y for each value of u of y and for x, okay, just to make sure that I've done my math right, and they're all 2, which is what we wanted. Okay, I'll come back to this value here in just a second, but here I've plotted the joint probability distribution, kind of, okay, but this is meant to represent the joint probability distribution. So this curve right here, right, this curve that I've drawn is this black curve. So if I could kind of tilt, if I could tilt this plot to where I was even with like the x or u of y axis, this black line would start to come, as I'm going up, it'd be low, and then as I got into these higher contours, it would go up and up and up, and then down, 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 okay? And that's what this is representing right here, okay? And then I want to find the mean of my u of y samples, right? Which is the values of u of y when y equals 2, and it's 1.80, okay? So this one might round to 1.81. Again, that's because of the sampling bias. But this value, right? This value is the same as what we got for our analytic solution here, as well as for the, where are we? So it's what we got for the analytic solution, okay? And when I multiply 3 times, when I plug that back into my formula for the expected value of x given y equals 2, I again get 0.6, which is what we found for the regression. Okay, so anyway, so this is just different ways that we could have approached that problem. Okay, the final one, this video is getting way too long. Okay, the final one is, it says advanced. Okay, so we want to find the best value of y given that x equals 1 and z equals 3. We may wish to use the technique of multiple regression, where we're trying to solve this guy right here. Okay. So what's happening here? What's happening here? Let's come up. Back to our DAG. Okay, so we're trying to solve for y given a causal variable as well as an effect variable here. Okay, that's all we're doing. Back down. Okay, so this is a little bit mathy, but as per our hint, we want to find these regression coefficients given here. Okay, and so I'm just going to call them beta x and beta z. Okay. Now these formulas are given in the book for for equations 1.27 and 1.28, and so basically everything in here. So I won't go through the math. I'll let you do that. But basically every term in here, okay, so the covariance of y and x and so on, we have found previously in this problem, okay? The only thing that we did not find is the variance of z. Okay, so here's how we find the variance of z right here. Okay, so if z is y over 16 plus u of z, I can take the variance of both of those. I can take the constant out. That should be 1 over 16 squared is what that should be. I'll fix that I'll fix it right now. Okay, so anyway, the variance is this ugly fraction right here. So I'm going to plug that back into to my formulas. Okay, I've used R to calculate it. All right, and so when you do that, you get about 0.33 and 0.06. Okay, so now if I plug those in, to this equation right here, okay, then I have the coefficient for x times the value of x, which is 1. The value for z, which is 3 times its coefficient, and we come out with approximately 0.52. You could get a very exact decimal answer if you wanted, but anyway, I calculated all of this here. Okay, so this is the exact answer. All right, and then we can also check this with simulation. So I'm regressing y on x and z. We're told that there's no intercept here. Okay, and to this point, I've been assuming an intercept and just generally been finding that it equals 0. But this one explicitly is not using an intercept. So in R, you can just make a 0 right here for that. And so I'm going to look at the coefficients calculated from here, and then look at the expected value given our sample data. So I go through. Okay, so the coefficient that is estimated from our data is 0.32, which is pretty close to 0.33. And then 0.06 or 57, which is very close to that. Okay, and then when I look at the expected value from our sample regression, I get 0.497. So it's close, but not perfect. And you don't expect it to be perfect with data. Okay, this has been a long one, so I hope you stuck with it.